Hello friends, in this video I will talk about the improvements in monolithic active pixel sensors for high energy physics experiments. So this is a follow-up of my previous videos on semiconductor detectors for high energy physics experiments. So MAP sensors, it stands for monolithic active pixel sensor. It is a based on CMOS technology. It's known as complementary metal oxide semiconductor. It is based on p-well and n-well structures. As it's shown here, you have n-well and then we have a p-well n-well structures. So to understand this complicated structure, first we have to understand the MOSFET structure. So for the MOSFET, there are two types of MOSFET. One is enhancement type and the depletion type. So in this MOSFET structure, you can see that we have a source terminal, gate terminal and drain terminal. We have a substrate which is basically of, in this case, is p-type, and then we can make the doping of n-type in this structure, and then we have a gate terminal. So we in this particular configuration, you can refer to any standard graduate book to understand it more in detail. So I will just give an idea how it works. So there is a channel created between source and drain that allows to flow the drain currents. So there are two cases. In one case, we create this particular channel that allows to a flow of current by applying some bias voltage between source and gate. Then we call it enhancement type. If it is already connected and there is already some way channel is created, then we call it depletion type. So now the next one more thing you can learn here. The shortest dimension of the gate is known as the technology. Like we have gate in 3 dimension will look like it, and we have the 2 dimension length and width. The shortest of the two is known as the technology, basically referred to as technology, the dimension of the shortest of the two. Like in this case, length is shortest. So when we say 65 nanometer technology, this is the length of that shortest dimension of the gate, and or 180 nanometer also referred as the same. So now CMOS pixel sensors. So CMOS pixel sensors consist of a detector part, then we have a front end electronics on the same die, on the same wafer. So to understand this structure, first we have to understand how it is formed. So first we have a low dope, low p dope, low density p type layer. Then we have a high density p plus layer. This is just to improve the ohmic contact. We always put the high doped layer at the before putting to the contact on the bottom, because to this improve the ohmic contact. Similarly, this structure we have also n type doping here. So when we dope here and with n type, there will be a depletion region created. So that is basically bell type depletion region, and we have a very high doped region, n-type region here to improve the ohmic contact again. So then we have a transistors here. This particular is called as NMOS transistor because we have a p-type substrate and then we have a n-type doping, so it's known as NMOS transistor. So you can see here also p-type structure, and then we have a n-type doping here, and then we have a gate also. So this is basically NMOS transistor, and then we create a deep p-well, and then that allows to create also PMOS transistor and also again NMOS transistor. So we have a detector here. This part is detector. So when charge particle comes here, it will first diffuse because there is no electric field in this region, then it will comes here and that will create the signal. Then that signal can be transferred to this complicated electronics to convert into the ADC. So this whole electronics is embedded on this chip. So this complicated structure now you can visualize as a detector, and then we have a front end electronics. Now this we show normally here NMOS, PMOS and then NMOS structure. So there's one purpose to show these particular structure, because now you can see here I can create here NMOS PMOS and NMOS again. So any complicated circuit will require either NMOS or PMOS transistor. So this is just for showing purposes that we can create NMOS and PMOS structure. So in the complicated circuitry, it will consist NMOS and PMOS both type of transistor, and that can be embedded in this particular section here. So we also create a deep p-valley structure here because the reason for it, it creates a barrier for the charge created here that confines the charge in this region, and charge will not flow in this region if you create a deep p-well. Another thing, the reason for creating the deep p-well, that it allows to create the N-well structure also, that is basically PMOS transistor here. Then the technology nodes. So why what is the importance of technology nodes? So around 1971 we have a 10 micrometer gate length, and then it's further reduced. When we say the technology, its length is shortest dimension of the two, and then we reduce it as you can see in the years it is reduced. Now we talk about 65 nanometer technology, which is on which R&D is going on for high energy physics experiments to use as tracking detectors. So to give a more idea, people are currently working on 5 nanometer level, just doing R&D, but this is not feasible at a very larger scale, but this is again people are working on it. And just to give one more idea, the shortest dimension of the gate is created is 1 nanometer by putting a carbon nanotube at the place of gate. This is done at LBNL. You can just see the link I will put in the description. So why we want to go at the lowest technology node? Because if you just see the technology nodes and the pixel size, that there's a 20 factor. So if you have a lower if you have the lower gate length, then that allows to create a pixels of lower size, and that will ultimately reduce the uncertainty in the measurement of the coordinate which we want to measure in the experiments. So this particularly, if we go to a lower lower size of the gate dimension, then that will allow us to create a lower size of the pixels, and that will ultimately reduce the uncertainty in the measurement of the coordinate. And then the improvements in the maps. So there this particular structure I already explained. We have a p-type lower density p-type layer which we call as a substrate, and then we create the n-type doping, and then n plus, because to improve the ohmic contact. And then this particular structure will create the depletion region of bell shaped, and then we have the PMOS and NMOS transistor here. And then this deep p-well, as I mentioned, it's constant a charge in this region. It will not allow to charge enter because of the large barrier. And so further there is an improvement in this technology. Like you can just see here, we have only n-type in this region. Now if you want to have a larger depletion region, then you have to put n doping. That will create the depletion region in this region also. That's what is optimized in the software. So people put low dose and type of implant in between of the whole region. You can just see up to here. That allows to create the depletion region very large. You can see in this region, the depletion region looks like this. Due to the low dose and type implant, all other things are same. Then we have the all transistors and MOS transistor that allows to create a complicated circuit structure. So in this case we have a fill factor of 100%. We don't have any dead region. If your charge comes here anywhere, it will be collected. So Now this particular structure is already published. I already put the link in this DOI. I will put in the description also. So there is a work ongoing now further to improve the time resolution of these sensors to make it comparable to the oil gas sensors, which will be the very best for these types of sensors. Then we will have a good coordinate measurement and as well as the good timing performance. So these types of structures, so just for your information, can be optimized using Silvaco software or Centerus TK software. So this is all. Thank you.